next speaker, and I met Dr. Kao here last night. We've been corresponding a little bit, and I'm very excited because he's an expert on using Mathematica, and I'm telling you, you want to talk about a steep learning curve. So I'm really glad to have somebody I can ask questions to about that. He's also new to the NPA and is going to be talking today on non-locality, which is, I guess, the issue of can we have action at a distance or can we not, and it certainly has relevance to the ideas of quantum mechanics. He told me last night that he found out about the NPA about 10 years ago, and he always has had problems with relativity, but it took him this long to finally get here. So we're awfully glad to have you here all the way. He lives in Canada now, but from China originally, Dr. Guanjun Kao.
Yep. How do you use the mouse to click? Oh.
That's it.
Oh.
This is forward,
Forward.
reverse, and that's you.
What's that? Okay.
Fix the screen.
Okay. This is the first time I'm here, so let me begin with a brief self-introduction. But before that, let me say thanks to Mr. Volk, Mr. Harrison, Mr. Atchison, and all other organizers whose hard work will make this conference a great success. So here's my name. There's four letters there. I work for Georgia College and date the place of my birth. I'm a Canadian, but I was born in China. So my interests include mathematics, physics, religion, philosophy, a lot of them. Today, unfortunately, I'm going to show only one of you, only one to you today. So I'm going to talk about a new type of non-locality in quantum mechanics, and also to say something about the physical implications of that. So first, the background information. So in my presentation include background information, theoretical assumption, evidence, and then I draw major conclusion. And after that, I explore the physical and philosophical implications, and I make some further discussion. Last but not least, I address the question of scientific attitude, if I have time. So first, let me say something about light speed or light speed constancy. A lot of people are interested in this, I believe. Okay, we have this well-known formula from Maxwell's theory, right? And from this, the formula clearly shows that light speed is determined by the electric and magnetic characteristic of the vacuum. So we conclude that light speed is a media property. And so if it's a media property, it's not affected by observer motion nor source motion. However, because it is the observer who is making the actual measurements, so his or her motion must be taken account into. So that's why we have a dependence on observer motion. Okay, let's write an equation of propagation for light. It's quite simple. Because light speed is a media property, and so the thing matters is the source position at source position at the signal emitting time, and receiver position at signal receiving time. Only those two pieces of information are important to us. So that's all we need to figure out how long it takes for the light signals to finish the trip. Okay, it's quite simple. Propagation equation. Okay, and then from this equation we can derive something interesting. For example, measure the speed of light, c plus or minus v, relative to the observer, not to the source, as I said, independent source, okay? And then let me next do this, a couple of, let me do a couple of, how do I click this? I'm sorry.
Cases? You won't go forward?
No, click the case 1, case 2.
I don't know.
It's not, so it's not working?
You're clicking on the pointer. You want to click on the slides?
Click on the case 1, you see the hyperlink?
Oh, it's a
Can
link.
you
It's
maybe
a link.
somebody else can.
Oh, I see. You want me to click on the one?
Yeah. You do that. Can you do that for me? And then,
Alternative one?
no, not alternative. Case 1.
I did, but nothing happens. Oh,
Oh,
there it
yeah.
goes. That's
No,
okay.
no.
Oh dear.
That'll be a problem. Okay. Then we solve a case.
Sorry.
So that ask you to test the demonstration. That's mathematical demonstration. I will show
Do
you.
you want me to go to the other file?
Okay. Let's all go to alternative anyway.
The Mathematica file?
Okay. So yeah, the mathematical file. That's right. That's right. Okay. Then now there we go.
I'll get it.
Yeah.
Okay, I knew this was coming. All right, I have them all in one file for you. I may have to evaluate. Hang on. Just make sure. Okay. Yeah.
I'm sorry, I really time consuming.
It's okay. I've
No,
got it.
organized.
I've got it here.
Yeah, just for the first one. Yeah, just
Unfortunately, it's
yeah, come.
just a second.
Run the animation.
It doesn't work to the left as I
No,
told
you
before.
don't. You don't
But it
go
works
that
here.
way. Which is automatic. Click the plus sign.
Yeah.
No, this one. This one. Yeah, click that. And then the arrow, the thick arrow,
Okay.
thick arrow.
Okay.
Yeah. Okay.
I know this.
Okay. Sorry. This.
It's a lot of pressure.
Okay. It's reversed.
It only works
Some-
halfway. I'm not sure.
So. Okay. I'm sorry.
You want to go the other
this
way?
one. Yeah, the other way. Can you do that?
I don't know.
The first
How about the other one? The other one.
Maybe. I'm sorry.
Anyway, the other one.
It's
the
going
bottom.
backwards.
Click the back one.
It's okay.
Remove the back one.
It's okay. It's okay. We see that.
There we go. Okay.
No, sure. Oh yeah. Here we go.
Now it
You
goes-
see it? Yeah. So that light speed. Light depend on our observer because the observer moving to the right, he receives the right signal earlier than the left. Okay, that's quite clear. Then the other one, the
I think the
demonstration.
next one does not work.
Okay.
I told you this before. This one doesn't.
Try
work.
it. Yeah.
I
Otherwise we.
apologize. I'll try it, but I don't think it works. I'm sorry.
It's okay. It's okay. Click on PDF then. Alternative. I have alternative.
Okay. Do you
file.
want to see
Yeah.
this now, or is this?
No,
This is
still
later?
repeat. Go back. Let me go back.
Keep it open.
Go back to the file, the main file.
This one or
No,
not?
main file. I'm
Sorry.
working on the main file, right?
I'm doing my best here.
Yeah.
Okay. Do I have the right? Here we go. And let me.
Yeah.
Which slide are you on? Do you know? Are we? Where are you at? Am I close? I'll try to. Is this? Am I in the right place?
Go
Am I-
back. Go back. Okay.
can
Let
you-
me.
Okay, go back. Can you go back? I can.
Let me go back.
Are we pretty close? I went to about slide 9. Figure that's was a good guess.
Something.
There we
Okay.
go.
Yeah. Here we go. Anyway, yeah. Click alternative 2. Okay.
Okay.
Okay. So I can do that actually.
Yeah.
Oh, let me see.
I don't think that does it.
No. Click alternative 2. Is working.
I'm sorry. It's not doing.
Okay. Then.
This too? Maybe I'm clicking the wrong. There we go.
No, so it's moving to the next. Anyway,
Sorry.
I believe it's easy to understand that. Okay, let me move on. Okay, so sorry about that. We
Sorry.
didn't coordinate it well. So, okay, let me.
You should be able to go on now.
Let me go to the next page. No, it's not
Can't
moving.
do that?
Huh? Go, move
Someone's
on.
got to
Next
control it.
page. Yep.
There we go. Okay. Good.
Yep. Good.
This is
Now.
where you want to be?
What's wrong?
Go into circles? Go, the bottom
No.
one. The bottom one is to go forward.
No, so I'm going.
It's the top, I guess, if you're holding on something.
Seems not working. Oh, I'm sorry.
Well, I'm sorry. You're right. It's not working. Oh, there we go.
Ju-
Hang on. where you want to be? Okay.
Yeah, next let me say something about the principle of relativity.
I think you're going.
Oh, sorry.
Yeah.
I think.
There you go. Now you're on.
There we go. Yeah, I know some people are against the principle of relativity, but what I can safely conclude that it's not the principle of relativity is wrong, it is Einstein and other people's understanding is wrong. So we can fix the problem, and this is how we do that. And I will skip the detail because it's quite abstract. And then let's take a look at some example. We can understand this principle well. So example 1. Radio signals sent between two planets in the solar system do not reveal this system's motion relative to the center of the Milky Way. And that's the content of the principle of relativity. Okay, and another example. Example 2. Signals sent between an Earth-born antenna and an Earth-born receiver do not reveal the Earth's motion relative to the sun. And this belongs to the content of principle of relativity. So we see two important examples. And also there's another equivalent formulation. Remember, those are equivalent formulation based on revised or new concepts. You cannot just take that for granted, okay? In order to make them true, okay? Continue. And next, let me introduce non-locality, the concept. So what is non-locality? By definition, it refers to an interaction or influence that goes beyond the local space-time region. I use the relativity term, okay? And this means the existence of a faster than light influence. Superluminal means faster than light, okay? Examples, well-known examples of quantum correlation of entangled particles, but people sometimes people fail to realize that interference pattern in a double-slit experiment also belongs to non-locality. In this presentation, I will particularly focus on this, quite a new one, the way how objects are physically connected. That belongs to the content of non-locality. It's quite a new one, okay? Brief comment, non-locality directly contradicts special relativity. That's why special relativity is wrong. Okay, we will mention other aspects of relativity which is wrong. Okay. So next, let me introduce the ECI frame. This refers to Earth-centered inertia. Let's imagine the Earth is rotating around the sun, at the same time it spins on its axis. Suppose somehow the spin stopped, and then we have an ECI frame. That's the realization of ECI frame. And by the way, sorry. By the way, the ECI frame is associated with the GPS range measurement equation, short for GPS RME for short. I will say more about the GPS range measurement equation later. And next, SSBCI, that refers to solar system barycenter inertia. Barycenter means the center for mass, of center of mass. And this SSBCI is associated with the interplanetary range measurement equation, and IPRME for short. And sometimes we approximate the SSBCI by SCI, sun-centered inertia, because most of the solar system mass is concentrated in the sun. Next, let me say the theoretical assumptions I made to draw the conclusion. Okay, here's the first one. If each of the GPS RME and the IPRME can be true, then they can be true at the same time. Don't take this for granted. For example, somebody flip a coin, get a head. Another person flip the same coin, get a tail. You cannot get head and tail at the same time because those results test separately. That's the same situation. Those equations test separately. I have to show both true at the same time to draw the conclusion. Okay. And yeah, as I said, this is non-trivial assumption. And next, I use absolute simultaneity. This is not my assumption. The scientists working in the field, they make this assumption implicitly, absolute simultaneity. And that's against the special relativity again. Okay. Next, the law, Newton's law of gravity, subject is second order, higher order revision. Okay, so, and that's the three pieces of the three assumptions I make. Remember the Newton's law of gravity. That's how we obtain the fundamental orbital information for the sun, for moon, and all planets. The orbital information called ephemeris. Okay. Yeah, experimental evidence. Here are three pieces of them, experimental evidence. The first one is GPS range element equation. Here's we go. It looks familiar, right? We saw that before. And also we have interplanetary range element equation, and so also looks familiar. But this time there's two pieces of them because light signal transmitted from the antenna on Earth and to a planet and go back. So there's upper lag times, there are down lag light times. Okay, there are two equations. But you can see that those equations, all the three equations are the same equation rewriting. The before the equation I introduced before is variation, essentially the same. Okay, so the first equation, GPS range environment equation. The simplified form. I dropped the error term, okay? The error term dropped. And it's referred to the ECI, Earth-centered inertial. And because the GPS range environment equation uses the fact that light propagated in the ECI with the constant c, okay? While the interplanetary range environment equation uses the fact that light propagates relative to the SCI with the constant c. Be careful. And the first one, c refers to ECI. The second one, c refers to SCI. Those are important facts we use. Okay. So lastly, here's the Sagnac effect in the GPS, and we know the Earth's orbital motion is not detectable. However, the self-rotation is detectable, and that effect we call Sagnac effect in the GPS. Okay, that's the three pieces of key information I use to draw a conclusion. Okay, here's not moving anymore. Can you help me again?
I don't know. Just keep trying. Maybe you got some extra characters in there?
Maybe once. Oh,
that's me.
yeah.
I'm just
Yeah,
trying.
you click. No?
I don't know.
Okay, here we go.
Finally did something.
Maybe.
I think there's some extra characters in there.
Yeah, comment. Let me make a couple of comments. The GPS RME explains the null result of the the Michelson-Morley experiment. The IPRME, interplanetary range measurement equation, explains the astronomical phenomenon of stellar aberration. Okay, and the reason that the GPS range RME explains null result of MM experiment because we use the fact that light propagates in ECI with a constant. That fact explains MX easily. Okay, and let's take a look. I guess you can click on the stellar aberration. Let's see if it's working. Yeah. Yes. Oh, sorry.
What? Okay, is it the PDF
Yeah.
file?
Anyway, so okay.
PDF file?
Yeah, PDF.
I have it. Hang on. Is it?
No, the other one.
The other file or the other?
The other file. The other file.
Oh, the.
No.
Okay, not this. All right, hang on.
Should be all together.
The
Right?
Mathematica file. Is that what you want?
No, PDF file. Just all there. You right? You combine all the file there, right?
Yeah, they're all in one.
Yeah.
Is it? Tell me what you want.
Yeah. So you see the stellar aberration? This is how we explain stellar aberration. You see the parallel lights, star lights, parallel, and Earth is moving in this direction. And the stellar aberration is explained by the transverse motion of the Earth relative to the incoming lights. Okay, and so tan alpha equals to this. We get V sin theta over C, and the maximum V over C calculated to be 20.6 seconds something. Okay, and the p factor used here is light speed C is relative to the SCI frame. That's why the IPRMFE explains stellar aberration easily and simply, beautifully. Okay, so go back.
Go back again.
Yeah.
Let's see.
Me file.
No. Which slide are we on now?
Yeah, here. It's just
Give me
this
a
one. Just
number?
this one. You see that?
This one
Oh,
here?
you did.
That's the right
Yeah,
one?
just slideshow.
Okay, all right.
Slideshow.
All right. I hope I'm on the right one. Is this?
Okay, then next. Yeah, other.
Are we a ways behind? I don't know.
Okay, I have not drawn the major conclusion yet. Okay, let me go back. A minute. Okay, thank you. Yeah, so I will.
Is it quite a ways ahead? Are we close?
Yeah, let me anyway first explain the major conclusion.
Okay. So.
Okay, not yet. Go back again. Yeah, major conclusion. That's my focus of today's lecture. If I finish that, well, everything will be fine. Okay, so here's major conclusion. Here's the simultaneous truthfulness of both the GPS RME and the IP RME. That implies non-locality. Or equivalently, we can say this. Light speed's independence of source motion, that's one principle. The other one is the principle of relativity in its modified form in this presentation, in this paper, and that implies non-locality. So the first two, so basically say the same thing. So I have simulation. Let's try to go back to mathematical file this time.
Mathematical file?
Yeah, the simulation, not
yes,
alternative.
I think I know what you mean.
Mathematical demonstration.
Yep.
Hopefully this will succeed.
This one? This one?
Yeah, that's this one. Run the animation now.
Okay.
Click it. Yeah. Yeah, beautiful.
Oops, I'm sorry.
This one, that's the major conclusion. No, something wrong.
Not moving.
Not okay.
I don't know. Maybe my computer's slow.
Okay, now let's go
Sorry.
to the PDF file then. Can you go to the
Okay.
go back
Yes,
to the
I can.
PDF file?
Just a
I'm
minute.
sorry, there's so
I'm
many
sorry
mistakes
to-
because a lot of
It's not-
insertion not coordinating well.
I
I thought
apologize.
everything. Yeah, go just try to find the PDF file. The other one. Yeah, here. Here we go. Yeah. Anyway, it's like a simulation. You see at the initial moment, OO prime, the coincide. Okay. Now at this moment, light signal is sent. You have two spaceship SS prime. Okay. So then move on. Now I use the yellow one. The yellow one. Sorry. Can you go back?
Yes.
Yeah. This frame connected by a solid line, and now frame by dashed line. So they have different physical connections. That's why that explains why light propagates according to different mechanism. And then the dashed line, and that's propagating according to light speed's independence of the motion of light source. And the solid one frame propagating according to principle of relativity. And it seems that the light signal seem able to detect those two different kinds of connection. That's what we call non-locality. And what is most strange is when the photons, when the light signals go to their destination separately, it seems they know their destination beforehand. Okay, that's why, and it's strange, but that's the necessary conclusion I draw. Okay, and that's non-locality. Okay, we can, if anybody interested, we can discuss it later. But I believe this is sound, the conclusion. Okay, let's move on then.
Back to the
How many
presentation.
minutes left?
Presentation again?
Yeah,
Okay.
20 minutes. How many minutes? Can you show me? 5. Good. Good. I'm fine. Yes.
Okay. Again from here.
Just a slideshow. Slideshow will be
Okay.
Yeah.
Hopefully you remember, please. We did this.
next one. If the GPS range measurement equation represents the physical law, and then the GPS RME and the GPS Sagnac effect. Okay, GPS range measurement equation, and same time the GPS Sagnac effect means non-locality. Okay, let's do the simulation. This is not working. Just go direction to the alternative. We will have time to finish that. Okay. Yeah. The PDF file.
Yep. I'm there.
Okay. Okay, here we go. Two spaceships you see here, two spaceships. And that one's connected with the Earth, the center of Earth. This one connected with the Earth by a solid line, means it's part of the Earth, like a fixed on the Earth, or use a platform to support. While the other one is connected with the Earth by a dashed line, that's orbiting. That spaceship is orbiting the Earth, okay? And then the light will propagate according to different mechanism, and we can draw that conclusion. You see here, and then this spaceship, so this light propagates with a constant speed relative to the non-rotating frame. That's where Sagnac effect comes into play, okay? The red one. And while this one is orbiting the Earth, and then the light propagates with constant relative to the spaceship itself. That's why we say orbital motion is not detectable. You see, the two means non-locality. Why non-locality? You see the experimental experimental apparatus inside here. The immediate environment of the experimental apparatus same, but since somehow light photons can detect the connection, different connection. Otherwise, you cannot explain why they propagate according to different mechanism. Okay, that's non-locality. Anyway, I finished the most important things. But let me anyway go back to the major, and I will just address the scientific attitude. 2 minutes. Okay. Yeah, go back to the. I will skip the physical and philosophical. We can discuss later. Show slides. No, go back.
One more.
Let me do it. Okay, 2 minutes, I hope.
Sorry?
No, so I need to escape. Escape.
What do you want?
You don't do
stuck in a loop?
I'm escaping those. I'm going to the last one.
Okay.
I'm going to schedule this. I don't have time. 2 minutes. But escape this, okay? I'm sorry, so sorry.
It's okay.
The coordination is not right. Sorry. Okay, yeah, last but not least, anyway, I know that, no problem. And as people's attitude towards science is sometimes really concerned. I want to specifically mention this. This is not just mainstream physics. It's also include ourselves, okay? We first need dedicated to truth itself, not to dogma or self-interest or anything else, okay? And second one, we should be open and objective-minded enough to be able to evaluate both the pros and cons of everything. We want to face negative, not just positive. Otherwise, we can get truth, okay? And continue. And we should be courageous and forthright enough to admit making a mistake and to correct that. And whenever possible, we should see things as they actually are, not what we believe them to be, because facts are life of science. And then when we criticize others, we should uphold the same academic and moral standard as have been demanded of those being criticized. And lastly, when I derive the conclusion in this paper, I follow all the above guidelines. If you want to challenge me, to please do the same. Okay, and one reference, all other reference found in the paper, in my paper. Okay, this is new reference. Okay, thank you very much. I'm honored to hear paper.